In a cell, the activity of enzyme have to be regulated. A substrate cannot be constantly converted into its product. So the cell contains natural molecules that act as inhibitors of an enzyme. Inhibitors are also extremely important in medicine because a lot of drugs used to treat disease are in fact inhibitors of specific enzymes. In this video, what we will do is look at the impact on Km and Vmax of three classes of inhibitors that form transient interaction with an enzyme. The first class of inhibitors is called competitive inhibitors. These inhibitors bind to the enzyme and prevent the binding of the substrate to the enzyme. We have already discussed one of these competitive inhibitors. We called it a structural analog. You remember it's a molecule that has a structure very similar to the substrate and can bind to the active site of the enzyme. There are other types of competitive inhibitors, but all of them bind to the enzyme and prevent the binding of the substrate. What does it mean? It means that we have formation of either an enzyme inhibitor or an enzyme substrate complex. And the formation of these complexes, as well as their dissociation, have their own rate that can be defined. And we will see how we define them. We can make a prediction. When we add a given amount of substrate, we will have formation of an enzyme substrate complex, but we will also have formation of an enzyme inhibitor complex. So the concentration of enzyme substrate complex will be lower in the presence of the inhibitor than in its absence. And that suggests that the enzyme will have a lower affinity for its substrate in the presence of the inhibitor. So we can predict that Km will increase in the presence of an inhibitor. The second feature is that as we increase the concentration of substrate, we'll have a higher concentration of enzyme substrate. There will be a competition between the binding of the substrate and the binding of the inhibitor. Because the concentration of the inhibitor is constant, then as we increase the concentration of substrate, the substrate will outcompete the inhibitor. Therefore, the enzyme will reach the same maximum velocity when we increase the concentration of substrate, whether or not you have an inhibitor present. So we can expect that the maximum velocity will be unchanged in the presence of a competitive inhibitor. Let's try to demonstrate that. If you remember, we've defined Km as being the concentration of E, the free enzyme, times the concentration of substrate over the concentration of enzyme substrate. And we've defined that based on steady state conditions. In fact, the steady state also applies to the enzyme and its inhibitor. At steady state, the rate of the formation of the enzyme inhibitor complex is equal to the rate of the degradation of this complex. So we can also define a constant called Ki, which is the product of the concentration of inhibitor times the concentration of enzyme divided by the concentration of the enzyme inhibitor complex. If the second step of the reaction, the conversion of the enzyme substrate complex into product and enzyme, is the limiting rate of the reaction, we can say that when Ki is high, the enzyme has a low affinity for its inhibitor, and when Ki is low, the enzyme has a high affinity for its inhibitor. Now we have two equations, one for Km and one for Ki. Once again, what we are trying to do is to eliminate from these equations terms that are difficult to determine. In our case, it will be the concentration of free enzyme, the concentration of enzyme substrate, but also the concentration of enzyme inhibitor. If we calculate the ratio of Km over Ki, we can eliminate one of these terms that is difficult to determine, the concentration of free enzyme. Now we have just to eliminate two other terms, the concentration of enzyme substrate complex and the concentration of enzyme inhibitor complex. So we can rearrange our equation now to get Km over Ki times the concentration of inhibitor over the concentration of substrate equals the concentration of enzyme inhibitor complex divided by the concentration of enzyme substrate complex. To convert this ratio, EI over ES, into something that is easy to determine, we need to go back to our toolbox of equations. Remember the velocity of the reaction? V0 equals K2 times the concentration of the enzyme substrate complex, and Vmax equals K2 times the concentration of total enzyme. We also have the concentration of total enzyme, which is the sum of the concentration of free enzyme, the concentration of enzyme substrate complex, and the concentration of enzyme inhibitor complex. Now we can replace in our equation the concentration of enzyme inhibitor complex by the concentration of total enzyme minus the concentration of enzyme substrate minus the concentration of free enzyme. And if we rearrange the equation, now we have two ratios that we have to take care of. One is the ratio between the concentration of total enzyme divided by the concentration of enzyme substrate complex. And the second is the concentration of enzyme divided by the concentration of enzyme substrate complex. How can we get rid of that? Remember that if we calculate the ratio between Vmax and V0, it is in fact the concentration of total enzyme divided by the concentration of enzyme substrate. So this ratio in our equation can be replaced by Vmax over V0. Now when we express Km, we can rearrange the equation for Km and say that Km over the concentration of substrate equals the concentration of free enzyme divided by the concentration of enzyme substrate. Now we can replace this ratio in our equation by Km over the concentration of S. Now our equation becomes Km over Ki times the concentration of inhibitor over the concentration of substrate equals Vmax over V0 minus 1 minus Km over the concentration of S. So if we take a closer look at our equation, we can see that now we have two variables, V0 and S. And the rest is constant. Km, Vmax, the concentration of inhibitor, these three values are constant. So we can now rearrange this equation, trying to put 1 over V0 on one side of the equal sign and the rest on the other side. And what we get, 1 over V0 equals Km over Vmax times 1 plus the concentration of inhibitor over Ki times 1 over S plus 1 over Vmax. This equation looks familiar. It is the equation of a straight line, y equal mx plus b. But it's also familiar because it resembles Lineweaver-Burke equation. In fact, this equation is the Lineweaver-Burke equation in the presence of an inhibitor. So if we compare the Lineweaver-Burke equations with and without inhibitor and look at the plot of the straight lines, we can learn a certain number of things. For example, so the intercept between the vertical axis and the straight lines are, in the absence of inhibitor, the term b, 1 over Vmax. But it's also 1 over Vmax in the presence of inhibitor. And as predicted, Vmax is the same with or without inhibitor. Now let's look at the slope the slope in the absence of inhibitor is Km over Vmax. In the presence of inhibitor, it's Km over Vmax times 1 plus the concentration of inhibitor over Ki. This term is larger than 1, which means that the slope in the presence of an inhibitor will be higher than the slope in the absence of the inhibitor. So the straight line in the presence of inhibitor will be steeper than the straight line without inhibitor. Now what about Km? So first what we can do is replace 1 plus the concentration of inhibitor over Ki by a constant called alpha. And so our equation becomes 1 over V0 equals alpha Km over Vmax times 1 over S plus 1 over Vmax. If we look at the intercept between the x-axis, the horizontal axis, and the straight lines, we can see that it will be minus 1 over Km in the absence of our inhibitor, and it will be 1 over alpha Km in the presence of the inhibitor. So the apparent Km in the presence of an inhibitor is alpha times the Km in the absence of the inhibitor. And because alpha is larger than 1, then our apparent Km in the presence of inhibitor is higher than the Km without inhibitor. That is also what we predicted.